Good afternoon, everybody. Let me introduce you to our work machine learning methods for predicting the lattice characteristics of materials. So for the safe and effective use of materials, we need to know their thermal and elastic properties. We can, of course, measure these properties from experiment, but experiments are often slow and expensive. So we can calculate these properties using some theoretical approach. And here we have two options: ab initio methods, which do not contain fitting parameters but time consuming, or we have model approaches which are fast but require some material specific parameters. In this work, we suggest using machine learning methods to predict material specific parameters based on known information in order to make model approaches more reliable. We use data on 5,244 crystalline compounds from the Open Aflowlib repository to build machine learning models which enable to predict important features of phonon spectrum of material, such as the bi-temperature and Grunizing parameter required for simulation of its lattice properties. We use two descriptors. The first one is pseudo-binary, where each column corresponds to a certain element of the periodic system from the entire list of elements in all compounds that make up the dataset. The numerical value of each of the columns for a given row is equal to the number of atoms of a given element in the chemical formula of the compound. The second descriptor is physicochemical. It contains data on the properties of atoms, such as mass, electrical charge, covalent radii, and electronegativity, and data on its crystal structure, the distances between the nearest neighbors, and the average volume per atom. We use different machine learning algorithms: gradient boosting, random forests, artificial neural networks, and support vector machines. We have performed optimization of hyperparameters of models using the randomized search CV methods, and we split our dataset into two parts. 95% was used to train the models with a 5-fold cross-validation, and the rest 5% of the data was used exclusively for model evaluation. For evaluation metrics, we use root square mean error and the coefficient of determination. Here you can see regression results using a pseudo-binary descriptor. We can see that in the case of the bi-temperature, the best performance is shown by the neural networks and the gradient boosting. We see here the highest coefficient of determination and the lowest root squared mean error. But if we look at the Grunizing parameter, we see that here neural networks show much worse performance, from which we can conclude that the choice of machine algorithm method depends on the target property. If we look at the results for the test set, we hear that overall performance, of course, is lower. This is because this is a true prediction on the data which has not been seen by the model. Now we come to the regression results using a physicochemical descriptor. We hear that overall here the performance is much better. We see for the coefficient of determination for the bi-temperatures, the value is higher than the 0.9, and overall the best results here are shown by the gradient boosting method. We see here it's on both the coefficient of determination, which is the highest, and the root square mean error, which is lowest. So here you can see the predicted versus true values for the prediction based on gradient boosting and physicochemical descriptor. And now we come up to the conclusion. We show that the characteristics of the phonon spectrum can be predicted using machine learning algorithms. The descriptor that contains information on the physicochemical properties provides better accuracy than the pseudo-binary descriptor. The choice of machine learning algorithm depends on the target property, and the most accurate predictions have been obtained using a model based on the gradient boosting algorithm. Thank you for your attention.